Hello, welcome to the video. Today we're going to be looking at section 4.6 where we're going to look at the fundamental theorem of algebra. So in this lesson we are going to be able to determine whether a polynomial equation has any imaginary solutions. So up to this point we have only had equations or functions that have given us real solutions or real x-intercepts. Now, there are some instances where you're going to have an imaginary number. An imaginary number is anything that has a negative square root. So we're going to note this, and anything that has square root of a -1, you are going to turn that into the variable I, and that's going to stand for imaginary. So if you ever had something like in a result, for an example, like the square root of -4. Now, if you typed in square root of -4, you would get like a code error, syntax error, domain error, something like that in your calculator. So what you gotta have, basically what you're gonna have to do is kind of break this up into two parts. Like this is the square root of -1, and this is the square root of 4. Well, square root of 4 is 2. Well, more specifically, it's plus or minus 2, and the square root of -1 is I. So it's essentially square root of -4 is plus or minus 2I, and that's considered to be imaginary. Fundamental theorem of algebra basically states this is anytime you have a polynomial and where the lead degree is n, you are going to have that many solutions, whether they are real solutions or if they are imaginary solutions. If your lead degree was to the fifth power, you're going to have 5 solutions. Whether they're real solutions or imaginary solutions, that is yet to be determined. You also have to take into account uh, repeated solutions like we talked about in the last section, where anytime you have a square of a binomial, even though you may have 5 solutions or something to this extent, but one of them is like x plus 3 quantity squared, yes, you're technically only going to have 4 solutions, but because they're repeated, it's actually 5. So keep that in mind. So in this particular question, they want to know how many solutions does the equation have? It's not asking for what they are, it's just how many solutions it has. All right, I look at my degree here and it's 3, so there are 3 possible solutions. How many zeros? It's the same, it's asking the same question. A and B are asking the same question. You just look at the lead degree, which is 4, and it's 4. All right. When they get into asking find all the zeros, prior to that they were just asking to find the real solutions. Now they want you to find all. So that is both the real solutions and the imaginary solutions. So here's how we're going to go about solving this. So what I would suggest you to do is get out your graphing calculator and let's type this in. So I go in and say, all right, I got x to the fifth power plus x to the third power minus 2x to the second minus 12x minus 8. And then I make sure it's in standard and I graph this. All right, so I look at this and it looks like Looks like negative 1 is in fact a solution. But if you notice that it looks like it just touches the x-axis, what that means is anytime it just touches the x-axis, that means that it is a square of a binomial, which is a repeated solution. So essentially, it's a possibility that negative 1 will be written twice. So here we go. Let's do this. Let's try, looks like 2 could be a solution. Let's try 2 right off the bat. That'll make things more fun. So we got our 2, so now let's prove it using synthetic division. So I got my 1, I got 0 because there's no x to the 4th, 1, negative 2, negative 12, negative 8. 5, 4, 3, 2, 1 constant. Okay. Drop down the 1, multiply it, I get 2, add them together, I get 2, multiply those together, I get 4, add them up, I get 5, multiply this, I get 10, this becomes 8, I get 16, negative 12 plus 16 is 4, multiply that by 2, I get, looks like 8, and that's 0. Cool. So 2 is a solution. You know, that's great. All right, now let's give negative 1 a try. So drop down the 1, I go negative 1. This gives me 1, I go negative 1. Here, this gives me 4, I get negative 4, I get 4. Multiply that by negative 1, 4, 0. Checks out. So now I've found all of the real solutions that I can find because this is, remember, written as twice because it's a repeat. So I have 1, 2, 3. So 1, 2, 3. I need 5 total, so that means there are 2 that are imaginary. So let's take a look at this here. This is my, constant value, x to the first, x to the second, x to the third, and let's see what we come up with. So I go here, 1x to the third plus x squared plus x plus 4. So it's a 4-term polynomial, so we got to go and group it. So I go here, I can take this as x squared, and this becomes x plus 1. And then, oh, this will be 4. Plus 4x. And then I can take out a 4 here, and this would be x plus 1. So they're the same here and the same here. So now I can take x plus 1 times it by the quantity of x squared plus 4. So what this did is, yes, I knew it was going to be repeated, but now this validates that it is written twice because I got this x equals negative 1. So that's just part of this repeated portion right here. So now I got x squared plus 4 is set equal to 0 with the 0 product property. X squared equals negative 4. Take the square root of both sides. Now this is where my complex number is, and x is going to be both positive and negative 2i, which was kind of what the example we did on the first page. So I have 1, 2, 3, 4 with the repeated negative 1, and then 5. So my all real solutions are going to be positive 2. So x would equal positive 2, negative 1, positive 2i and negative 2i, knowing that if you wanted to write negative 1 in twice, that's fine, but know that that is a repeated solution. So just like in previous lesson, we talked about an irrational conjugate theorem, we have a complex conjugate theorem. Same idea that even when you have um, an imaginary number as a solution, you're going to write both the positive and the negative of that zero of the function. Here is what that is going to do. So since we know that I is going to be equal to the square root of negative 1, that means that anytime you see I squared, you're automatically going to write it as negative 1. Because if you just went here, oh, this is squared and this is squared, I squared stays the same. The square root and the square cancel out. So remember that when you're doing a problem like this, and it's going to help you out when you need to find the answer to those particular problems. So with that being said, we have, they want us to find a polynomial function of least degree that has rational coefficients and a lead coefficient of 1, where my zeros are 2 and 3 plus I. Okay, so what we have to do is this, the 2 is pretty straightforward. You just write it as 2, or sorry, as x minus 2. Then what you are going to take into account, because 3 plus I is that imaginary value, you were going to write it as x minus, and in parentheses, 3 plus I. And then you're going to multiply it by x minus, and in parentheses, 3 minus I. So from here, I'm going to basically distribute the negative. So this x minus 2 gets, just kind of comes down with the right in the math. So this becomes x minus 3 minus I, and this becomes x minus 3 plus I. Now I'm going to regroup it. So I got a group here and a group here. What that does is I can now write this as a sum and difference pattern, because again, like this is the minus and this is the plus. So x minus 2 still comes down. This is now going to be x minus 3 quantity squared minus I squared. Now, we talked about anytime that you have I squared, you're immediately going to replace it as negative 1. So now it's going to be x minus 2 times it by, this is going to be x minus 3 quantity squared. This is now going to be minus negative 1, which actually is going to be plus 1. So now from here, I got this x minus 3 quantity squared. Use the sum of the two. Use the sum of the square of binomials, or the difference of the square of binomials. In this case, it's going to be x minus 2. And then this is going to be x squared minus 6x plus 9 plus 1. So this turns now into x minus 2. Combine these like terms here. So this is going to be x squared minus 6x plus 10. Now, just like what we did with the conjugates, now we just multiply this out. Take this x, multiply it by the 3 terms to the right. It becomes x cubed minus 6x squared plus 10x. Cross that out. I got minus 2x squared plus 12x minus 20. And then it's just a matter of combining like terms. So the x cubed remains the same, no change. Here and here with x squared, so it's minus 8x squared. Cross it out, cross it out. With x to the first would be what, plus 22x and minus 20. And that is being able to solve the fundamental theorem of algebra. Hope this helps. Until next time.